We're starting chapter 17, which is about probability models. We're kind of going to start with some context here. So, searching for tiger. If you remember a while back, we had an example that used a cereal manufacturer who puts pictures of famous athletes on cards in boxes of cereal. 20% of those are of Tiger Woods, 30% are David Beckham, and 50% are Serena Williams. You just have to have a tiger card and therefore start opening box after box. Every time you open a box, that is one trial. There are only two possible outcomes. It's either a success, you get Tiger Woods, or it's failure, you get Beckham or Williams. The probability that you succeed is 20%. And the trials are independent, so opening one box is not going to affect you opening the other box, or at least what card is in the other box. Situations like these are called Bernoulli trials. Common examples of Bernoulli trials are tossing a coin, looking for defective products on an assembly line, or shooting a free throw. To be specific, Bernoulli trials have two outcomes. You either succeed or you fail. So in the previous context, we either got Tiger Woods' card or we didn't. You have a fixed probability of success, so your probability can't change. And in this case, opening one box, you had a 20% chance of getting Tiger Woods. Opening the next box, you still had 20% chance. And then independence from trial to trial. So 3 things make something a Bernoulli trial. You have 2 outcomes, you have a fixed probability of success, and your trials are independent. Looking at an example, we're going to be searching for Tiger. We want to know what is the probability that Tiger's card is in the first box you open. Well, there's a 20% chance of picking Tiger's card, so the probability for picking Tiger's card on the first try is equal to 20%. What is the probability that you get his card on the second box? So this is the probability that you get Tiger's card on the second box. So this will end up being equal to, you don't get his card the first time, so the probability you don't get his card is 80%, times the probability that you do get his card, which is 20%, which is 16% of the time. The last one is what is the probability that you get his card on the 5th box. So this would be the probability that we find his card the 5th time. So that means that the first 4 boxes do not contain Tiger's card. So that would be 0.8 to the 4th, representing the probability of not getting Tiger's card, and that the first 4 boxes are not his, times 0.2 when we finally do get his card, which ends up equaling 0.837, or 83.7% of the time. Searching for Tiger. Looking at another example, how many boxes might you expect to have to open? Please note that we're looking at how many we expect to have to open. That's very similar to our expected value, same concept as our mean. So in other words, how many boxes might you have to open on average? Since we have a 20% chance, we can reason that it's 1 in 5. So 1 out of every 5 boxes is going to contain a Tiger Woods card. This would mean that we would have to open 5 boxes of cereal. On average, that's going to be our mu, we're going to use our mean for mu, is equal to 1 over 0.2, which is equal to 5. So 1 divided by your probability is how many you would expect to have to open. This is a situation of the geometric model. A single Bernoulli trial is not that interesting. More likely, we want to know how long it will take to achieve a success. P is always going to be your probability of success, and Q, which is 1 minus P, is your failure. Because we either succeed or fail, if we know one probability, we can find the other probability. X is going to be the number of trials, and the mean is always going to be found by 1 divided by the probability of success. And then the standard deviation, which we use the sigma for, is the square root of your probability of failure divided by the probability of success squared. This brings us to independence. You need to check that the trials for Bernoulli trials are independent. If exactly 20% of the boxes have Tiger's picture, then technically getting 1 will have an effect. However, if there are a few million boxes on the shelf, then the difference is not really worth mentioning. If there are only 10 boxes of cereal, then only 2 contain Tiger's picture. If you open one and get Tiger's picture, then the probability that you get Tiger's picture again goes down, therefore they wouldn't be independent. However, if we think about this in reality, they're not only selling this box of cereal in one store or even in one state. They're selling them all over the place. Therefore, there's probably a few million, so opening one really won't affect the probability of the next one. This brings us to the 10% condition. Bernoulli trials must be independent. If that assumption is not true, so technically in our context, it's technically not true, but it's still okay as long as the sample is smaller than 10% of the population. So in other words, when you're doing a Bernoulli trial problem, you must actually check that they are independent. If they are not, then they have to fulfill the 10% condition, meaning that your sample size is smaller than 10% of the population. In addition, you must actually check that as well by taking your population and multiplying it by 10% and checking to see that your sample is actually smaller than that. Looking at an example, people with O negative blood are universal donors because they can give blood to any blood type. Only about 6% of people have O negative blood. If donors line up at random, how many do you expect to examine before you find someone with O negative blood? Again, this is our expected value or our mean, which is 1 over the probability of success. So the probability of success is 6%, so it would be 1 over 0.06, which is 16.67, or approximately 17 people. Since we're talking about people here, we typically want to round to a whole number, because you can't have 2/3 of a person. Number 2, what's the probability that the first O-negative donor is one of the first 4 people? This one is pretty tricky. We can really do it 2 ways. So we can find the probability that they are of the first 4 by finding the probability that they are the first, plus the probability that they could be the second, plus the probability they could be the third, plus the probability they could be the fourth. But that's a lot of work. It's less work because we have less trials right now, but if we were to say, what's the probability that they are one of the first 40 people, this would be a lot of work. So instead of doing it out this way, we can actually use 1 minus in this situation. So the probability that they are one of the first 4 people would be that they could not be there at all. They could be the first person, the second, the third, or the fourth. So we're looking for that probability, which does not include 0. And again, when you use the word not, that means we have to subtract from 1. So we would do 1 minus the probability of 0 O negative. So the probability that you're not O negative is 94%. So this would be 1 minus 0.94 to the 4th. So again, 1 minus because I'm taking out the 0, that's what I'm not including. The 94% comes from the probability of not having O negative blood. And the exponent of 4 is because we're looking at 4 people. So this becomes 1 minus 0.781 or 0.219, which is 21.9% of the time. So the probability that somebody will have O negative blood in one of the first 4 people is 21.9% of the time. We're going to practice using the geometric model more in class tomorrow, but that's all I have for tonight, so I will see you guys tomorrow.